Great. Thank you very much. It's really a pleasure to be here. This is my first trip to Singapore, despite having had 2 students and a postdoc from Singapore. So one of my former students is sitting in the back now. It's great to see him here. I'd like to thank the organizers. Zhidong, thank you very much. Joey, Shen as well, thank you. And the staff at IMS have been really wonderful. Eileen and everyone else who have taken care of us really deserve an enormous amount of thanks. So if I look a little tired, my body was really convinced that 1 a.m. was the right time to get up and could not be convinced to go back and take a nap. Yeah, I'm standing here, so if I lay down and take a nap mid-talk, you'll understand why. This is, first of all, a quick advertisement. I'm the editor-in-chief at the Journal of the Optical Society of America. Yeah, I'm a big guy. What can I tell you? I try not to let the power go to my head, Misha. Yeah, I'm often in the airport and someone runs up to me and says, "Oh my God, is it the editor of JOSA A?" And I say, yes, it is. But we very gladly publish inverse problems in optics, and Sentinek, whom I'm sure many of you know, is our topical editor for the subject. She's wonderful, and I'm always looking for strong contributions from outside the usual community who send things to OSA journals. This is work I started while I was still at the University of Illinois, and many of my collaborators are still there. My main collaborator on this work is Steve Beaupart, and members of his group, notably Dan Marks, who's now at Duke, Stephen Addy, who's at Cornell, and Yuanji Liu is still at Illinois, and a number of great grad students. Out of my own group, a number of incredibly strong students, these are sort of chronological, have contributed to this work. Dan was actually in my group for a while after having been in Steve's group. And then Steve and I formed a company, and this is also my disclosure that I have a company built around some of the work I'll show you today. But the company contributed back to the science. They ran a clinical trial, and I'll show you some images from the clinical trial in the course of this talk. We work with a number of incredibly good people, surgeons from around the country in the US, and the team who actually built the instrument in the company, really a great group of engineers and business people. So I want to first talk to you about optical coherence tomography. So if you don't know the subject already, so let me see a quick show of hands. Who knows what OCT is already? Quite a lot of you, most of you. Okay. So for those of you who don't, the short version is OCT is just echolocation. Okay, you send light out of typically a laser source, but not necessarily. Claude Bocara famously did OCT with sunlight, one of the more beautiful experiments I've seen in the last few decades. You send in scanning OCT, that is not full field OCT, but point scanning OCT, you send a beam into an interferometer of some variety, sending part of the beam to a sample, part of the beam to a reference arm. The light interacts with the sample, comes back into the interferometer, and is combined with the reference light at the detector. And the measurement originally was made in so-called time domain OCT by moving the interferometer arm and sweeping through a wave packet, if you will, in the coherence domain. This is not really how it's done in the modern age. In the modern age, we understand how Fourier transforms work, and it's much faster to just sweep the frequency and then take the Fourier transform at the end. But the data are equivalent at the end of the day. So if you do this with the beam sent into a sample, like so. By the way, this image is getting a bit thread-worn. It's about 15 years old. This was state-of-the-art 15 years ago, and from my friend Steve Beaupart's lab. But if you send a beam into the sample, like so, imagine going along this arrow right here, coming in from the top, scanning down to the bottom, and you scan in the time domain and just try to collect the envelope, right? And of course, you have to define what you mean by the envelope, but typically we take the complex analytic signal, and we take the envelope from that, and then we throw away the carrier, or at least that's what was done in the community, throw away the carrier and the phase and all of that. You extract the envelope, and the envelope encodes essentially the strength of the reflected field as a function, sort of depth into the sample. Okay? So you do that along one line, along one pencil, and then you do it again and another, and you scan the beam across the sample like this, building up these lines as you go. You stack the lines next to each other, and now you have a tomographic image of whatever you're imaging. Now this is the scoundrel's last refuge in the imaging community. It's a little zebrafish. No, actually, this is a tadpole. This is a tadpole, semi-transparent, incredibly easy to image, and you know, it's what everyone images because of that. So, okay. So OCT has been around now for a quarter of a century, and what's kept it around and kept it alive in the community, I mean, in a good measure of how alive it is that about half of the submissions to biomedical optics express in some way or another involve OCT. And one of the reasons it's stayed around is that early on it found purchase in the ophthalmology community. So this is an Olympus, no, sorry, this is a Zeiss instrument. You can see patient sits here, looks into an imaging system. Ophthalmologist sits here, looks at a display which is spitting out three-dimensional cross-sections, or cross-sections. In principle, you can do 3D rendering. Cross-sections of the patient's retina. So this machine that sits here has a bunch of moving parts inside of it that put the focus of the beam back on the retina and then sweep through either in the time or frequency domains to obtain these scans of the depth structure of the retina and then stack them next to each other. Okay? This is really a revolution in ophthalmology because you can get very early diagnosis of diseases of the eye and of the retina, which give you time to pursue early interventions and treatments, and it's been a huge success. But the thing I'd like to impress upon you is that this is, as my grandmother used to say, bigger than a bread box. Okay? This is a large instrument. And it is large because of the following problem. This is a sort of a standard test sample. This is an image made with that OCT, well, not the commercial OCT system, but the cartoon system that I showed you. These are actual data made by scanning into a pretty typical test sample. We took silicone, which is essentially clear in the spectral region we work in. We work in the near infrared, so around 1,300 nanometers. Silicone's clear. We embed in it a bunch of nanoparticles, in this case a bunch of zinc oxide particles. You use whatever you like. You just need a little contrast. You want the particles to be sub-resolution in your system so that they all wind up looking like spots. And the spots should all be the same size. And what you can see from this image is that they definitely are not all the same size. And the reason they are not is that the focal plane is down here, and light does not actually propagate along pencil beams. Light diffracts, light spreads, light propagates along beams. So, this is what you'd like to think happens in OCT. It is not. This is a pretty good approximation. If you're working at low resolution or low numerical aperture, this is a pretty good approximation to the pencil beam as long as you're in this region. And if you'd like to work at higher resolution, you got to consider that your field really does this. You focus down and it spreads back out, and if you're not paying attention, you wind up in the out of focus region very quickly as you try to do high resolution imaging. And that's really what got demonstrated back here. Focus is down here, that beam spreads out as we go up, and so the little points up here, you know, as you start down here, you see, oh, they're point-like, but as you go up, they get a little fatter and a little bigger. They also get a little weaker because, of course, that field is spreading and the energy is getting spread out. So the scatterers themselves aren't getting weaker, but the signal's getting weaker. And eventually, as you get up here, they start doing really weird things, right? As you get up here, they go all stripy, right? They not only get fat, they get stripy. And the stripiness is something that in the optical imaging community is often referred to as speckle It's a word that's a bit dangerous because people who don't really understand speckle attach magical significance to it, as though it is a phenomena that is somehow distinct from what you could predict with Maxwell's equations. It is not. It is an interference effect. And that's what you see here, that the field from these neighboring particles scatters coherently, and when you collect them in your aperture, they interfere, sometimes constructively and sometimes destructively, but they all share this signature pattern of interference, the stripiness that you see up in this region. And I'll show you some more examples of that are a little more dramatic in a bit. Okay, so the basic message is that an OCT pencil beam that we'd like to have is not actually the same thing as a real optical beam, but if you work at low resolution, it's close enough for government work. Okay? All right, actually, let me go back to something I wanted before we start doing math. So I want to go back to this instrument again. This instrument is the size it is because ophthalmologists need to see a level of detail that put you in a regime where you can have the entire retina in what is called the confocal region, in that part where the beam is a close enough approximation to a pencil beam as makes no difference. And you go ahead and scan it across the retina and everything works just fine. But you really have to have the focal plane centered on the retina as you're doing that. If you have it, say, in the middle of the eye, the retina winds up out of focus. They're at high enough resolution that a few millimeters off means that you're out of focus. Okay? And so this machine here has moving parts inside of it that move lenses. And those lenses reposition the focus so it's on the retina. All right? And that's necessary to get good images out of it. Right? So as I mentioned, the technology has been around for a quarter of a century. And for most of that quarter century, people have been talking about the coming OCT revolution in medical imaging. And as they say, you can only be promising for so long. OCT just hasn't found fertile ground outside of ophthalmology. And the real reason for this is that interesting things in physiology and in things that I work in, like cancer, happen closer to the cellular scale or at the subcellular scale, where you need resolutions that are closer to the wavelength, or really at the wavelength, which means you have to work at very high numerical apertures indeed. In which case, you need not only to move the focus sort of near your region of interest, but if you want to have any kind of depth of field, you have to keep moving the focus. So you have to have this big machine no matter what you do. And it turns out that if you want to do OCT, let's say, in surgery, patients really object to having something that large crammed inside their cavities. Okay? So, to this group, I'm sure the answer is obvious, right? Math to the rescue. So we do some math. And originally, we sort of attacked this problem and tried to formulate it as an inverse problem. And I could present it to you that way. But honestly, this is going to be the world's simplest inverse problem, which is good news, because if you want to actually make it work in a hospital, it's got to be pretty simple and easy to implement. But I really just want to show you the forward problem more than anything else. And the inverse problem is completely trivial once the forward problem is done. So here's a little cartoon of our system. I have an optical fiber, and it gets scanned back and forth. In fact, of course, we use little micro mirrors, little MEMS devices that scan the beam. And from that fiber emerges, it's a single mode fiber, emerges a Gaussian beam. Okay, it's got a Gaussian profile, and Gaussians are nice because when you propagate Gaussians, you get Gaussians. It's Gaussians all the way down. Okay? It goes through a lens. And that lens gives you a nice focused Gaussian beam with a focal spot somewhere down in a sample here. So light comes out of the fiber, light goes through a lens. All my lenses are flat. It goes through my lens. It goes down into my sample where I experience some inhomogeneity. Right? Now, I don't need to tell this group. I'm going to describe my incident field as being a function of this position of the fiber, a function of the position in space, and a function of k. K is the wave number. It's just the circular frequency, omega divided by c, if you like, okay? So, or 1 over, or 2 pi over the wavelength, if you like that. But it's a proxy for frequency. I have some term in front that takes account of all the power, because the spectra of the source is always, is never constant across the whole band. And we're going to use broadband light here. We're going to use light with about a 10% bandwidth. So we have light that's centered around 1300 and has about 130 nanometers of bandwidth. So this field propagates into my sample and experiences an inhomogeneity down here. And within the Born approximation, okay, so I immediately do the easy thing and linearize, right? So nonlinear inverse problems are of great interest here, but I only do the easy thing. I linearize and I say, okay, I'm going to create a secondary wave down here, and it's going to be proportional to the incident field, and some susceptibility eta, and some Green's function g, and the Green's function g is pretty easy to calculate. Okay, so then I sort of integrate over all the spots where that happens. So I integrate over all the Green's functions at all the inhomogeneities multiplied by the incident field at all those places. And then I do something that's a little bit tricky. So if anyone here does antenna theory, and I know a lot of people in the inverse problems community come out of EM theory, so maybe some of you will recognize this. This is really just what you would do if you had an antenna, a transponder, and you sent out a signal and then you brought it back. The receiver function is just equal to the thing that sent the signal out, right? So the thing that sent it out was a beam profile g, and the thing that you have to project against when you collect it again is the same stupid thing. It's that simple. So you have an aperture function g, sends the light out, collects it back, you integrate the field that's returning to the lens across that aperture function, and then that gives you some coherent signal, S. Now what I'm leaving out of this formulation is all the interferometry I explained in that first slide. Okay? So when you do the interferometry, the reason you do the interferometry is that you actually put your hands directly on the complex field, which is, or more to the point, the complex signal S. Okay, so I'm skipping right to that. There are a bunch of steps involving Hilbert transforms and invocations of causality to get you there, but it's not really worth going through. So, all right. So then the complex signal S, if I unpack this a little bit, has some power factor in it, has an integral over the aperture, has an integral over the volume of the scatterer, has a Green function in it, has another beam factor shape in it, has another beam factor shape in it, and then sitting at the end here is eta, and you can go ahead and formulate this as an inverse problem, and you've got 5-folded integrals there, and if you can discretize the whole thing and wait ages of the universe to try and do it numerically, or you can start cheating, which is what we do. So, cheating's always good. Cheating's the only way to do anything worth doing. So, the particulars of the optical system we're looking at are important here because they make life easier. They allow us to cheat. And I say it's cheating because in a minute I'll tell you where the cheating could catch you off guard if you're not careful. But we got very, very lucky. And if you're going to cheat, it helps to be lucky along the way. So we have a Gaussian beam profile here, G, which is typical of these systems. You could, in fact, there's a lot of interest now. We're working on formulating the same problem for these supposedly non-diffracting beams, which are never really non-diffracting because once you run them through finite apertures, but Bessel beam solutions, which are kind of interesting. You can substitute your own favorite flavor of beam in here. And that beam is characterized by some width, which, I'm sorry to make you sort of trace through the silliness here, but the width of the beam is really a function of the wavelength and the numerical aperture of the system. And the important thing to take into account here is that the width is inversely proportional to the numerical aperture. Again, this crowd doesn't need to be told that the Fourier transform of Gaussians are Gaussians, and that's what makes it all really nice. And when you multiply Gaussians, you get more Gaussians. The Green function is very simply the standard. So I'm doing everything here in scalar approximation. If you'd like to be tortured with the full-blown tensor electromagnetic stuff, you can read the papers. But the important thing is that there's a nice Weyl decomposition into plane waves. And this factor kz is very important. This encodes the so-called dispersion relation of the system, which enforces that all of the plane waves in this system obey the wave equation and are therefore modes of the system. And so this kz of the transverse momentum q is just given by the dispersion relation. It's the square root of the wave number squared minus the size of the wave vector squared, like so. And this is really critical to the whole thing. And so I'd like everyone to kind of pay attention to that bit. It's the most important thing on this slide, that kz is root k squared minus q squared. Okay. So then you sort of stuff all of that back into this equation. I'll remind you of that. And this is where I say we cheat. I just start doing asymptotics, right? It's optics. So of course, anything interesting in optics comes out of asymptotics, or at least anything usable. I used to do near-field optics, and I can tell you it's not usable or that interesting. It's just painful, and you can't do asymptotics anywhere. So, all right. So you unpack all of that, and you find that if you take the Fourier transform of this signal, remember the signal is a function of where you put the light in and the wave number. You scan it around. Okay? So now you take a 2D Fourier transform of that signal. And it's still a function of the wave number. There's still a power factor out here. Now, of course, we've converted integrals over 2 dimensions in space to integrals in 2 dimensions in the wave vector, in the momentum space. This is a system that had translational invariance. So, of course, a couple of the 5 integrals have dropped away. So I've only got 3 left. Yay, that's progress. And I now have an integral over the depth into the object. Right? So this makes a lot of sense if you just look at the symmetries of the problem initially. Right? I've got an aperture function there that I'm going to have to deal with through convolutions. That's the integral on Q. And I've got an integral on depth, which I just can't get around because I've broken the symmetry on depth because I've got this system that sends light in and then light comes back. Okay? So, but that integral is kind of tantalizing because what I see is that I've got a couple of these plane wave-like factors that have squirted out here. Right? These are highly oscillatory. The kz's, as long as I'm not in the near field, right? I think Gang and I, we're all scarred by near field optics at some point. As long as we're not in the near field, the kz's are all real. And so these are highly oscillatory. So these sort of beg out for a stationary phase treatment, right? And as long as the center of the integration, the z naught, is far away from the origin, you've got your big parameter and things drop right out. If you happen to be near the focus, z naught's the focus here, right? If you happen to be near the focus, you can't do stationary phase on this stuff. But if you look down here, I've got this Gaussian envelope sitting here. And if you pay attention to the alpha here, you'll remember that alpha is inversely proportional to the NA. And as the NA increases, the point at which you're far away comes closer in. And so you can always treat the region close to the focus as though alpha is really large. And so now I've got this Gaussian envelope sitting there with a large prefactor in the Gaussian, and it just wants me to just integrate by parts and do the usual sorts of tricks. So that's what we do. There we go. We take 2 different asymptotic limits. So in the first asymptotic limit, we do stationary phase for these phase factors being large. And in the other asymptotic limit, we just take the value of the integrand around the peak of this Gaussian. And it turns out that they give you the same answer. And this is where, if you're going to cheat, Misha, you have to be lucky.
Well, I can lucky one day, but cheating all the time, I will eventually become lucky.
Yeah, so exactly. As everyone who plays the lottery knows. Exactly. So we got very lucky. And we refer to this within my group as the asymptotic miracle.
It's like playing lottery.
It is exactly like playing the lottery. This is playing the asymptotic lottery. And that may be a better name for it. Maybe we'll from now on call it the asymptotic lottery instead of the asymptotic miracle. I'm much more interested in cheating the poor than in religion. But so we see here that this prefactor actually changes, whether you go from the far zone to the near zone, whether you're near the focus or far from the focus. So it's not exactly the same in both cases. But it turns out the only thing that really matters in this result is this piece right here, that the 2-dimensional Fourier transform of the data in the frequency domain is proportional to the 2-dimensional Fourier, or the 3-dimensional Fourier transform of the susceptibility. This is the world's easiest inverse problem. It's division. Okay? So this is something you can hand, Ben. You can hand this to an ECE grad student, right, Ben? Yes. And say, divide, go implement this. No, I'm just teasing. But so you take your data, you do a 2D FFT, and you just have to go find the mapping from this grid onto this grid, and you're done. And in fact, we know what problems like that look like. Oh, by the way, this was hot, and just so you know that I care about this conference. Hot off the presses. This got sent to me by one of my current grad students this morning. I asked him to calculate the error in the asymptotic series, both asymptotic series, and then plot them. And this is the error associated with the near field. This is the error associated with the far field. And you see that they cross down here. They're both relatively small. The normalization here isn't quite right. Doesn't really matter. But there's a crossover point. And the point is that they're both approximations work in a large region in sort of the intermediate zone. And down here, the near field works. And out here, the far field works. So you always have something that works. And they all come down to this, that if you have, if you do the division, right? This is the solution to the inverse problem. I'm really embarrassed to say it in front of this group, right? But this is it. The solution to the inverse problem for OCT is simply that the susceptibility at Fourier coordinate Q and beta is some prefactor that frankly does not matter. You can leave it out of the algorithm. And then the original data set on this hyperbolic grid. And that problem looks a lot like something we all know extremely well. It looks just like the projection slice theorem, right? Where you take data on a polar coordinate grid and map it onto a Cartesian grid. But there you have the nasty business of the singularity at the origin of the polar coordinate system. No such problem here. We don't have that problem. We avoid that problem because we don't collect data on the DC anyway. We take a high-pass filtered version of the object. So this is very stable and very fast to implement. Gui?
It depends on the fact that your source has this Gaussian form.
Not in the far zone, okay? So in the far zone, you can actually, as long as your source is sort of confined in some plane, right? Then you always get this out. This is simply a result. It's simply a result of the fact that the Green's function has a plane wave decomposition, and you're projecting onto those plane waves. It's a little more complicated than that because this is a double pass system. You're going out and back. And so if it were single pass, there'd be no remapping, right? But because it's double pass, this funniness happens. And that's probably a good place to add in that, again, this is where we got very lucky. If you look at the bistatic case, so this is what people who do radar would call the monostatic case, right? We have an aperture from which we send out a field, and then we collect the field through the same aperture. Monostatic. If you have an aperture that sends out the field and another aperture that collects it, that's the bistatic case. And we've actually worked all of that out. It's painful. And in that case, the near field and the far zone resamplings are not the same at all. At all. And you really, it's a mess. And so I highly recommend sticking with the monostatic case. It's easier to build the equipment anyway. Yes?
But the approach, Scott, the approach doesn't depend on the fact that your sample is small. It's relative to
It's Born approximation based.
wavelengths and the form of the incident field. So you get
No, I mean, I'll show you images of samples that are millimeters thick, and the wavelength is a micron.
But in the regime, the Born approximation works.
Right. So this is a very common misunderstanding of what the Born approximation is. The Born approximation does not require that the sample is small. It requires that the sample is electrically small.
Right.
And that is not the same thing as small. So it turns out that in the near infrared, biology cooperates with you, and it happens to be that that's where I'm interested in doing work.
Do you care about the near field map? So you
God, no. I've spent my entire career trying to get away from near field.
You don't care about the diagonals?
No. Actually, it's a different talk. I believe I do still work in the near field, actually, against my better judgment, and have that talk on my computer too. But this is strictly far zone. The OCT stuff is all far zone. And it's really hard to bring a SNOM into the operating theater. Okay? So, but I think this particular method is interesting for people who want to go beyond the Born approximation, precisely because as you go deeper in, I mean, this was the idea behind the onion peeling approaches and things like this. As you go deeper in, you get more and more multiple scattering. And so the nice thing about OCT is you can take a very thick sample, biological sample, it doesn't have to be biological, and you can just start scanning in and looking for the point at which the multiple scattering turns on. And so then you can apply your algorithms in a way that that you can do weak scattering approximation near the surface, and you're going to need multiple scattering as you go in, and you can go through a transition region where you're kind of guaranteed that no matter what you do, it'll work a little bit, which is a nice way to work, right? Because you can see, oh, it's working a little bit, now I go a little deeper. We're actually doing this now. Because otherwise, when you're doing these highly nonlinear, beyond Born approximation techniques with real data from a really strongly scattering system, you get your data, and then you apply your algorithm, you go, well, it didn't work. Well, why didn't it work? Was there a regime in which it would have worked? Is there a parameter I'm mistuning? Here, you can work your way into it. You can put one toe in the pool at a time. So I think it's really a wonderful platform for that kind of work. Okay, so here are data. So this is, remember I showed you that sample at the beginning to just try and illustrate the problem with the beam. Same sample all over again. So this is, and the numbers are rather small, but these are in microns. So this is several millimeters of sample. The system being used here has an NA of about 0.1. The central wavelength is around 1300 nanometers. These are sub-wavelength particles, and we've imaged it with an OCT system. And what you can see is that the focus is up here in your panel 3, and there are a bunch of little dots. And in panel 2, the dots are starting to go stripy. And the stripiness is because there are actually 2 dots sitting here, and the signals are interfering with each other. And then it goes here, and it gets checkerboardy. And that's because we have multiple things that are interfering with each other, making checkerboards. It's all just coherent interference. Okay? So you take and you go ahead and you do this to it, you do this algorithm to it by taking a Fourier transform, resampling the grid. It's just straight up interpolation. You can do nice spline things to it and stuff like that. And this happens, which is what should happen. Okay? And when I'm feeling sad about my job, I pull up this one and I go, oh, that's nice, and then I do that. And that's what it should look like. Okay? So this gives us the opportunity now to take a high NA OCT system, leave the focus wherever it happens to be. In fact, you can even do it with no focus at all and just run this thing through a pinhole, but you pay a signal price. Okay? At any resolution, you have an infinite depth of field, which is something system designers sort of go all bleary-eyed when I tell them about, because it means that you can design a compact system. What started out as an exercise in mathematics ends up as a result in mechanical engineering, because you can throw away all the bits and pieces of that big box that require you to move lenses. Right? You don't have to move lenses anymore. Leave the lenses where they are and compute things instead. So this is breast cancer. This is histology made under a standard light microscope after the tissue has been stained and sliced and diced. Okay? This is just for point of comparison. This is current state-of-the-art in medical care. This is unprocessed OCT data from slices just outside of the focal plane. This guy is slice A is about 1.5 millimeters outside of the focal plane. Slice B is about 0.5 millimeter outside of the focal plane. And the Rayleigh range here is about 100 microns. So here are the Icm reconstructions. And what's important about this, and the reason I put these comparison images up here, is that what you see here in the H&E, and these are not one-to-one mappings, because these images were obtained with tissue that had been cut out and then just imaged with an OCT device, okay? These images were obtained from the same piece of tissue after it had been soaked and fixed in paraffin and sliced. So the morphology changes a little bit, okay? But the idea here is that you should be able to see the lipid cell walls pretty easily, and you can here and you can't here, right? And you should be able to see what's called the necrotic boundary there, and you can here, and it's a little hard to discern here. And this is completely useless. And this is something where you can see cells and boundaries, and it's clinically useful. Okay? So the distinction here is that you now have something where you can just focus your system in, scan around, and get clinically useful images over a large depth of field. And this is a game changer for the utility of OCT in medical imaging. This is the thing that we were waiting for 2 decades. Okay? The thing that takes you beyond ophthalmology. This is somewhat trivial, but I think it's a nice example of why this can be important beyond the surgical theater. This is also important for people who do physiology. There was a minor controversy in the OCT literature about the size of sweat gland ducts. Okay? So this is an image of a fingertip. You might recognize that this is fingerprint. Okay, so this is a so-called en face image here. This is OCT. This is Icm. Yeah, the Icm looks a little bit crisper. That's fine. But if you look at the 3D rendered image, this up is actually going into the fingerprint. So it's as if I had my hand like this, and someone came in and imaged like this. Okay? It's not my hand, actually. It's a grad student with good skin. Okay? So the controversy in the literature is this, that if you read the physiology books, you know that the duct glands, the ducts for the sweat glands in your hand, should be about 60 microns in diameter. They're these corkscrew tire-bouchon, about 60 microns in diameter. And when you image these things with OCT, in order to get the resolution you need at the gland itself, the beam spreads so much that by the time you've imaged the corkscrew structure, the duct looks like it's twice as large as what the physiologists know it should be. So, can we fix this with our approach, which we call, by the way, it's a mouthful, interferometric synthetic aperture microscopy, ISAM. That's why this says ISAM. So this is just our algorithm, ISAM. Okay? So here's the OCT image, blurry mess. Here's the same data set. Here's the ISAM image. And if you take an en face cut of both of these, what you find is that up here, the cross-section of these little corkscrew structures is bang on the 60 microns it's supposed to be. And in the OCT image, it's 120, just as had been found in the literature. And so if you're doing quantitative physiology, these sorts of things matter. And people who do quantitative physiology also do pathology. And so it's critically important that you get the microstructure of your sample right. Okay. So I mentioned I'd show you some stuff from the company. We spun out of these results. This is a handheld probe that Diagnostic Photonics makes. And what you can see is that when you throw away all the bits and pieces that move lenses, you can make something that's significantly more compact. In fact, we could make it smaller than this, but we wanted something that would actually fit comfortably in the hand of the surgeon. If you make it much smaller, they start fumbling around with it. We're currently implementing a laparoscopic version of this that's considerably smaller still. Okay? But the trick is that all of the lenses are glued in place. There are no moving parts. Well, I take that back. There's one moving part. It's a MEMS device, a micro electromechanical mirror that scans the beam in 2D. Okay? It's tiny. Sits behind that glued together lens stack and scans the beam over the sample. The whole thing looks vaguely like an ultrasound machine in that we put it on a cart. There's the probe. There's a monitor. It goes in an operating theater. We've done a bunch of clinical trials with this, which have now been published. This is breast cancer. I'm afraid the projector doesn't quite do it justice, but I think you get the idea. This is what we call good news. This is just adipose tissue. Imagine this image blown up on a high-resolution display about this big sitting in the hospital. You get a very clear view of what is healthy tissue here. This is also healthy tissue, this sort of strand-like parenchyma structure, and this is tumor. And it turns out that if you give a surgeon about half an hour to 45 minutes with a large training set of data and let her just look at images that are labeled good and bad, she comes out of that able to distinguish cancer from non-cancer about 95% of the time. Now, what about the other 5%, you might ask? Right now, one of the principal problems we're trying to fix is that when surgeons go in and remove a breast tumor, about 1/3 of the time, they leave behind some cancer. And they don't know they've left behind some cancer until the piece they've cut out is sent out to a pathologist. And the pathologist does that H&E stuff I showed you, right? They stain it, and they fix it, and they slice it, and all of that takes a lot of time. And so you get an answer 3 or 4 days later. And that's a terrible time to say to a patient, you know, we missed a little and we have to go back in, because that's the point at which it really hurts. It's sore, the incision is just starting to heal up, and you really don't want to tell a person that you didn't quite get it all at that point. So what we're trying to do with this technique is actually catch those 25 to 35% of the cases where a little bit of the tumor is left behind. And if we can get 95% of those, we're really hitting a home run. At the end of the day, the tumor will still get shipped off to H&E, but if we could have 1/20th the number, if we could cut the number of patients who have to go in for a second operation down into the low single digits instead of the mid double digits, it would be a big improvement in the treatment of breast cancer via lumpectomies. And it really all hinges on the solution to an inverse problem. So, I don't know how I am on time. I may have gotten us a little bit back on track. There are a bunch of slides after this one if you want to ask technical questions. But I think, yeah, I like to make friends. I tell my undergraduates that I have never, ever been to a talk where someone in the audience has stood up and said, I loved your talk. I wish it were longer. So I'm waiting for that day. And we can make it as long as you want. I can stand here and do this all day. There's plenty of technical material that comes after this. But I'll say that the very important thing to recognize here is that this is the age of computed imaging, and it is so because this is the age of computers. When we originally wrote this algorithm, we ran it on a quad-core CPU, wrote it in MATLAB, roughly the same size data sets we're working with now. It took overnight to run one frame, okay? And we just did it, this 2D cheat version, one frame ran overnight, 12 hours. In the commercial implementation now, we're running it on GPUs, right? So if you've got kids at home and they're little zombies sitting in front of their video games, thank them. They're saving lives. They're financing the development of GPUs. And that's what we run our algorithms on. This screams out for parallelization, right? So the GPUs now run 8 frames at once because we actually do a genuine 3D reconstruction so that the resampling, the interpolation is actually done on a genuine 3D grid. So we run 8 slices at once and take the middle 2. And we do that at a rate of about 40 frames per second. So 8 frames 40 times per second, down from 1 frame in 12 hours. Okay? And it's really a consequence of the computing power that has changed so rapidly in the last decade that we can do this now, and this is commercially viable. And so for everyone working on inverse problems, keep working on inverse problems, because as they seem hopeless to implement in real time, the computational scientists are catching up. And they're catching up at an extraordinary rate. My last PhD student actually now works for NVIDIA. He had offers from KLA-Tencor and Apple, and they all paled by comparison because NVIDIA saw what he was doing and said, come to work for us. And they made it worth his while. Okay? This is where the future is. It's in computed imaging and the solution of inverse problems. And it's because the folks building computers are doing it so marvelously. Of course, he paid a price to get there. He had to learn CUDA. So, but you take a grad student, you give him a little water, and you feed him once a day, and you chain him to his desk. And you say, you can't leave until you know CUDA. Miracles happen. So it's fine. It worked. Data and image processing really must be coupled to physics. There's a big push now to do everything, sort of, if I have a big enough random forest, the machine will learn everything for me. Bullpucky. You have to learn the physics, and you have to teach the machine the physics and build the physics into your algorithms, and then you can do miracles. I really think that we've just sort of nibbled around the edges of the way we can encode in optical imaging anyway, structure and spectra together simultaneously. In my group right now, we're working on spectroscopic imaging in a vein very much like what I just showed you here, but trying to separate out different chemical species with some strong priors on how many species are there, and then do the sort of physics that I showed you here today. In the battle of lens versus algorithms, algorithms are winning. It's really just something I put in there for the kids doing theoretical work. It's always nice to give them a pep talk. And there are lots of open problems just right around the edges of what I'm doing here. There are so many things that we're not smart enough to figure out that I think powerful mathematicians could figure out. There are things in reconstructing the full susceptibility tensor that are there. We've actually implemented this for polarization imaging, but we only get sort of 2 components, right? And there should be 6. And we're also doing this for Doppler imaging. And of course, Doppler imaging, when you think about it, I was very excited to see some of the stuff on motion yesterday, because the problem we're facing is that essentially as soon as you put motion in, you've got another dimension. You've got another degree of freedom and no more data, really. And so solving that problem is a bit sticky. We've made some progress with things that work, but I don't understand why they work. I think that the day is coming when, and maybe it's already here, when that probe I showed you earlier will seem sort of a ridiculous extravagance, and that everything will in fact sit on a chip. The source, the detector, and the algorithms that we're developing will sit on a chip, and you'll just drop it into the patient, and out will come the images you need. It'll find its spot, and out will come the images. 5 minutes, all right. And I'm really done. I'm going to leave time for questions. Thank you very much. Misha, hi. Hey.
So, yeah, you have questions, yes?
Hey, Hui.
Yeah.
No, you've ruined me. I can never use that line again. I can never say that again. I tell all of my students that. Now I can't say it anymore. I'll say, there's one guy who said that. Thank you, Hui.
Do you work only in frequency domain or in time domain?
It doesn't matter.
It matters.
It really doesn't.
But which data you...
Both. We've done this with both. It doesn't matter.
But basically, can you have the one-dimensional problem each time? You have one-dimensional.
Well, I mean, that essentially is OCT, right? I mean, OCT is the original formulation is a one-dimensional problem, and you just assume that your time domain data map directly to your structure, or if you take frequency,
scattering data, right?
Yeah, or you take your frequency domain data and you take a Fourier transform.
Because I have algorithms for 1D case.
Sure.
But they are non-linear, of course.
Actually, that might be interesting. I I mean, the problem is, and I didn't really go into this, but so we started looking at, here we go. We started looking at the full field problem, and full field's kind of interesting. So this is a genuinely 3D problem. And we kind of gave up on full. Full field's exciting because it's fast, right? You get a three-dimensional volume of data set with swept frequency really fast, right? And that matters for things that are moving and biological living patients. But the problem is that when you do that, you discover the multiple scattering corrupts your image much faster than when you're doing the scanned point. Yeah. That's because, of course, the multiple scattering is really important when it is three-dimensional. Because your photons go in and they rattle around a little bit and they come out over here and they get the photon that went in here gets detected over here. Very, very rarely does the photon that goes in here come back out on the same spatial mode. Right? So the spatial filtering effect means that actually the multiple scattering is not that important in one dimension.
I have very simple problems about 1Z.
Very good.
You can take a look.
You mentioned the Born approximation.
Yeah.
So electronics, what do you mean by electronics small? So,
sorry, what?
So you said the Born approximation is good when so the change is electronically small.
Electrically small, yes, yes,
so
yes.
How do you, what does it mean?
Huh. Oh God, I really don't want to answer the question. So there's a decades-long collection of scoundrels in the literature who have made their living writing almost entirely useless papers on when the Born approximation is good. It's horrific. I will only say that the Born approximation works when it works. And that this is the evidence that it works here.
One more question, yes, please.
It seems to me the matrix is the information in the Fourier domain where the elegant relation.
Yep.
It seems to me that mainly due to your assumption is the Gaussian beam.
In the near zone, that's true. In the far zone, it's really just it's completely generic property of the fact that you have a finite aperture. So if you go far enough away from your finite aperture, you'll always get that in the far zone limit, but you may not get it in the near zone.
So is there some way you can make that form, learn that form from the data? Maybe not that simple.
Yeah, perhaps. Actually, it's interesting. We actually do something like that. Let me put this. It's the wrong way. Oh, I knew I'd do it wrong. Hang on. We do something like that in, once, that's the wrong talk. Hey, Gong, here's my near field stuff. Sorry. We do something like that for a technique we call computational adaptive optics, where, here we go. Where what we've done is introduced aberrations into the system and then tried to identify those aberrations as a sort of iterative process. Because once you have the complex field, you might as well start multiplying in phase functions and fixing the aberrations. So that's what we do here. And we do it blind in the sense that we don't know what they are to begin with, although we assume a finite set of Seidel aberrations.
You can just use a few parametric form.
Yeah, it's a simple parameter search. It's not that complicated, although doing it in an automated fashion was a pretty significant result for one of my students. Yeah.
Okay, so we cannot continue.
Yes, please.
Thank you.
Thank you.